All right, and finally our last question. Of course, this question has to tie in with the last question of Chapter 10, so let's see what we're dealing with. So use the results of problem 10.34 to determine the power radiated by an ideal electric dipole, P of t, at the origin. Check that your answer is consistent with the equation 1122 in the case of the sinusoidal time dependence with problem 1126 in the case of quadratic time dependence. Okay, we got some fancy looking words, so let's be aware. To start, for our solution, the fields of the non-static ideal dipole problem 1034 contains terms that go like 1 over r to the squared, and then 1 over r cubed for fixed time t naught equal t minus r over c. Radiation only comes from the first of these. Again, the radiation zone has 1 over r terms. The square and cubic terms do not radiate. They die off too quickly, so we don't care about them. So with that, the radiation fields look like negative mu naught over 4 pi r p double dot minus r times r dot p double dot, and b is equal to negative mu naught over 4 pi r c r hat cross p double dot. All right, so where the dipole moments are evaluated at t naught. The 1 over r squared terms from the pointing vector is s over r, the radiation vector. So we just have er cross br and, cancel away accordingly. So factor out whatever we need to. And now we're just left in the squiggly brackets with p double dot minus r dot p double dot r hat cross r hat cross p double dot. As you see, we're set up for a back cab method. So we distribute the cross product, and from that, from after distributing the cross product, now we can just apply all the back cab rules we want. First one, as you see, we get a pretty expected result, and now we can cancel a p double dot r dot p double dot with another r hat dot p double dot with a p double dot. So that's kind of nice. Then we see we just have a duplicate of the r dot p double dot. So we're left with two terms in the squiggly brackets, both in the r hat direction, so we can factor that out. No biggie. And then in that last step, before we factor out the r hat, we just go ahead and actually square the parts in the denominator for a reason that'll become apparent soon. So if we setting the z-axis along p double dot, we see that the square brackets turn to a p double dot squared sine squared theta. Reason why is because that dot product gives us a p double dot square cosine squared theta. So if we factor out the p double dot square, then we're left with 1 minus cosine squared theta from the dot product, and then that 1 minus cosine gives us the sine squared. We used a similar tactic like this a couple questions ago. But nonetheless, the power radiated comes from integrating the radiating pointing vector with its dA. So of course we have a 2 pi coming from the phi integral, 0 to 2 pi for the phi integral, 0 to pi for the theta integral. And you see the differential element gives us r squared sine theta d theta d phi. In purple we get the 2 pi. We like that. P squared constant, move it out. So we have sine to the third. We've seen that 1,000 times. And so we cancel away. We cancel a factor of pi, and that 2 reduces that 16 to an 8. And then sure enough, we get mu naught p double dot squared over 8 pi c times 4 thirds. So that 4 reduces that 8 to a 2, but then we have to multiply by 3, so that's where we get the 6 in the next step. And indeed, we have a mu naught p double dot over 6 pi c as expected. Cool. So for the sinusoidal case, we have p is equal to p naught cosine omega t. If we take the double derivative, we get a negative omega squared term out, typical with these sinusoidal cases. So what we say is that we have p double dot is equal to p double dot squared is equal to omega to the fourth. The negative signs cancel, of course, in the square. P naught squared cosine squared omega t. And its time average, well, the cosine time average goes to 1/2. So if we plug that in for the p double dot squared, In the time average power, we get mu naught over 12 pi c, since 2 times 6 gives us 12. Then we have omega to the 4th, p naught squared. And that again makes sense. We had omega to the 4th power for our radiations before. So this is in agreement with the equation 1122. And in the case of the quadratic time dependence, our results would agree with the answer to problem 1126. So, doing the same method, we're good to go. And we like that, so that's pretty cool to see. Later, guys.